What's up, peoples? This is a video to try and help you with a multi-object problem where the two objects will end up meeting at the same place at the same time, and their speeds are changing, and therefore they are accelerating. And so far I've drawn a picture to show that car A is moving to the east at 8 meters per second, and car B is moving initially to the west at 4 meters per second. But when you see that word west, that should be screaming at you that we need to make the initial velocity negative. A negative velocity means moving in the negative direction. What's interesting about this problem is that the speed is decreasing while moving left. So if you have a negative velocity and you want to slow down, you need a positive acceleration. Obviously, as we have talked about in class, when acceleration and velocity have opposite signs, it means the object is slowing down or decreasing speed. So since there's two objects, of course, by now you should know the strategy is to list your variables for each object. So, object A, the initial velocity of car A, the final velocity of car A, the acceleration of car A. And here's where it gets a little different. Because they meet at the same place, same time, they're the same final position. So it's important that instead of doing delta D, we write out initial position of A, final position of A, and the time it takes for A. I'm going to do the same thing with object B. I'll move it over here, I guess. Oh, I thought it was going to be green, but it's blue. Surprise. The initial velocity of B. This video will not be edited, so you are stuck with that. The acceleration of B. Again, we are separating initial and final positions. And delta T. All right. In the past, we have done this before where we separated the delta D into final and initial position. And since we're concerned with time and acceleration and velocities, or at least we know the initial velocity, we're looking at mathrep 3. Now, this was discussed in class where mathrep number 3 is simply delta D is initial velocity times time plus 1/2 acceleration times time squared. And what we did was that we separated delta D into D final minus D initial, and you have the rest of the equation over here, and then we moved the initial position over. So we got an expression for the final position, which is final position equals initial position, because I just added the initial position over, plus initial velocity times time, plus 1/2 acceleration times time squared. So by now you should know that this is definitely the expression you're going to be using for these very specific types of problems. So let's go back and fill in what we know. Notice I didn't number hunt. Like, okay, there's 8 meters per second. I got to write that down. Now I'm ready to start writing stuff down. I've got like my table is set, and I'm allowed to start putting dishes down, like my entrees down. I don't know if that makes any sense, but I did just have a cup of coffee, so maybe I'm going crazy. 8 meters per second. Don't know the final velocity. We do know the acceleration is 3 meters per second squared. I'm going to call the initial position 0 meters because that's where car A starts. That's all I know. Car B, which is blue, has an initial velocity of negative, that's important, 4 meters per second. Final velocity we don't know. Acceleration is, that's weird, positive 0.4 meters per second squared. I was saying it's weird because it's 4 meters per second and 0.4 meters per second squared. I don't like that. Car B seems to be starting at a position of 100 meters all the way on the right. We don't know the final position. We don't know the time. So right now, we don't know final position or time. We really don't have enough information to solve anything. But we do know, since they are going to pass each other, that the final position of A is equal to the final position of B. And the time that they travel, since it's ready, set, go, and then where do they pass each other, is also the same. And what a coincidence, we have this expression for final position, so we can simply set the expressions equal to each other since their final positions are equal to each other. So the first thing I'm going to do here is actually going to write that out. Some people skip this step. I like doing it. I'm going to take the expression here, and I'm going to write it here where it says final position. Some people go right to just setting equations equal, and that's fine. But I like writing this out. We have initial position of 0 plus 8 meters per second times time plus 1/2, squeezing this in, 3 meters per second squared delta t squared. I'm so sorry. That's like amateur hour here. squeezing that equation in. I'm going to write it for the final position of B, which, again, I'm just looking at the equation on the right here. And it says final position equals initial position, 100 meters, plus initial velocity times time, negative 4 meters per second, times time, plus 1/2 acceleration, 0.4 meters per second squared, times time squared. Again, this would seem on its own to be just one equation and we have two unknowns. That's a problem. But since the final positions are the same, we can set these two expressions equal to each other. It's so exciting. For me, anyway. I don't know about you. How you doing? You enjoying these videos? Are you watching them? Anyway, plus 1/2 3 meters per second squared, delta t squared, equals, I don't know why I shouted that, 100 meters plus negative 4 meters per second times time plus 1/2 acceleration times time squared. Again, the reason I can do this is I have an expression for final position. We know the final positions are the same. Therefore, we can set the expressions equal to each other. So what I'm going to do now is I'm going to combine like terms. And by like terms, we're talking like there's a delta t term here and a delta t term here. There's a 1/2 at squared term here and a 1/2 at squared term here. I can combine those. Don't let the units bother you. So when I combine them, what's a good color? Don't know. I'm going to go with green, sorry. I get 1.3 meters per second squared delta t squared plus 12 meters per second times time minus 400 equals 0. Now, we've talked about this in class already, but I do want to remind you, this is a quadratic. Here's your a term, because it's ax squared plus bx plus c. That's ax squared plus bx plus c. So your a term, b term, and c term. If you use the quadratic program, which should be on your calculator, you will get 2 times. I don't know the negative one because I didn't write it down before doing this video, but we are not going back in time, so let's go with the positive one. So we would get that delta t is 5.30 seconds. It's exciting stuff. Great. Now we can take that time, sub it back in, and solve for the final position. This is part of the reason I like writing it out, because now I could just sub it in to that equation, or I can sub it in to the equation on the right. And that's what I'm going to do right now. Are you ready? It's going to be fun. So you get the final position of A is equal to 8 meters per second times 5.3 seconds, 5.30 seconds, plus 1/2 3 meters per second squared times 5.3 seconds squared. Do you have to write the 0? No. I'm just letting you know that it was like 29 something, so I rounded it to 30. Don't forget to square. And I get that the final position of A is 84.5 meters. All right. I mean, it kind of makes sense. It was going to the right at a faster speed with a larger acceleration, and it was speeding up. And the other car was going west at a slower speed and also trying to slow down. So it would make sense that they would meet to the right of 50. Does this make sense? Well, let's find out. Let's see. I'm going to check my work. At the final position of B is equal to, and again, I'm just looking right up here at this equation, and I'm subbing in for time. That's what I'm doing. 100 meters. This is like the part where you're like, fast forward, times time, which is 5.3 seconds, plus 1/2 acceleration times time squared, which is 5.30 seconds squared. Oh, I forgot the 0 over there. Not going to be edited. And when I plugged that into a calculator, I got 84.4 meters. These two answers are the same. So that's about it, peoples. Let's do a quick summary, which I wrote ahead of time because I'm a genius. And I don't know why this is doing what it's doing. This will not be edited. All right. Oh my God. Apologies. So in summary, this is a two object problem where they meet at the same place at the same time. We've done problems before where they're two objects, but they don't meet same place, same time. Maybe how long do you wait for your friend? Or how much farther ahead is this person? Or something like that. But this is same place, same time. Usually phrased where and when will they meet? Or something like that. And again, we used the initial and final position instead of delta D. And we talked about how we used math rep number 3, and we separated delta D into df and di to derive that expression. And even though we don't know final position or time, we have an expression for final position that we can set equal. And a reminder that you should be careful with directions. Moving right means positive velocity. Moving left means negative velocity. And to increase speed, velocity and acceleration must have the same sign. To decrease speed, they have opposite signs. I know that seems weird, but you can be moving left with a negative velocity, have a positive acceleration, and slow down. All right, since we've created two expressions for the final position and the two objects have the same final position and same time, we can set them equal, solve for time. Once you have that time, you solve for final position. And that's it. These problems are pretty formulaic in how you solve them. You notice what it is, and you're like, yep, I know how to set this up. I'll use that magic final position equation and set them equal, and I'll do some math. So that's about it. Hopefully this was helpful in some way, shape, or form. And this one's pretty good. I'm going to give it a 3 out of 5 stars, and I probably wouldn't change a thing.